So we made a foldable for Newton's laws by taking a piece of paper and folding it in half and then cutting only one side. So we've got 3 flaps, one for the first law, the second law, and then the third law. So we're going to open up the first law. On the right-hand side, we're going to put what the law is, like we're going to define it, and then we're going to put our real-life examples here on the left. Does anybody remember what the first law was? The law of inertia? Mateo? Until what? Very good. So this is called the law of inertia. Objects at rest stay at rest. And objects in motion stay in motion unless acted on by an outside force. Force! You just applied a push to open the door. That door was at rest until you applied a force to make it move. Force! See, he did it again. My favorite real life example, and this is kind of morbid, but you know, like humans, we're really into this kind of stuff, car accidents. Okay? All right, so hear me out here. How many of you have ever been in the car, and be honest, how many of you have ever been in the car without your seatbelt on? All right, you don't have to be that honest. But what do you notice when the car stops? What happens to your body, Lexi? It jolts you forward, because when a car stops, the brakes are a force of friction being applied to the car. That force of friction, those brakes are not being applied to you, so you stay in motion. That's why people tell you that you could fly through the windshield if you don't have your seatbelt on. If you apply the brakes, you know, that's more gradual, right? But if you're full on accelerating in a car and you get in an accident, you have the full acceleration of the full force of that acceleration moving forward, also propelling or accelerating you forward, right? So if you're not wearing your seatbelt, you have no force to resist you. That's why your body continues to move, even if a force has acted on the car and made you stop. Does that make sense? Yes? Okay. Another example is driving. My car is going to stay stopped until I apply a force to start it. Yeah? It's also going to stay moving until force. It's going to stay moving until the force of friction resists it backwards and slows it down, right? Or I apply the force of friction on the brakes to stop it. Can anybody think of any other examples in real life that would apply to this law, Isaiah? Can you explain? Okay. Okay. I guess I started it with the violence a little bit with the car accident. So Yes, more appropriate. Thank you. When you throw a football, that football is going to stay in motion, right? Until the force of somebody stopping it with their body or hands. It's also going to not throw itself. You know, like your parents ever say, like, clean your room, it's not going to clean itself, right? That's because the stuff that's all over your floor is literally not going to move unless you move it. So, going to our examples, and if there's any other examples you guys can think of, please feel free to share them. If any of my mobile friends have some real life examples, anything with sports, really, anything with a ball, basketball, soccer ball, hockey, kickball, right? So that's how sports work. So driving, my car is not going to go forward or backwards unless a force is applied to it. Whether that force is the gas pedal, right? Or whether it's me pushing my car because I ran out of gas, it doesn't matter. If I want the vehicle to move, there has to be a force that's applied to it. I have pushed a car. Some of you may have seen me in car loop pushing cars before. So also wearing your seatbelt. Wearing your seatbelt applies a force to make you stop. So you don't fly forward. This is the same reason why if I have like a coffee in my drink holder and I slam on my brakes, but the drink moves and spills, but even though my car is stopped, because there's nothing stopping that from moving. And then we said like, sports is applied to all of these, right? All of these are applied to sports, but we're gonna say specifically like kicking or throwing a ball. Because remember, these are laws, they happen all at the same time. Just like I have to follow all the laws of the road at the same time. All of these laws of motion are also happening at the same time. Our next one, our second law of motion. Who remembers this one? Does anybody remember this one? Yeah, this one is where the math comes in. So here we go. To move a mass, you need a force. So to move any object that has matter, you need to apply a force to it. This is where that math equation F equals ma comes in. Force equals mass times acceleration. Yes. The idea is, if I want to move something with twice as much mass and have it go the same speed, what do I need? More force, twice as much force. If I want something that has, if I apply the same, or if I have something with the same mass, but I want it to go twice as fast, what do I need? Same amount of mass, but I want it to go twice as fast. What do I need? More force. If I have something that's speeding up and I have, if I want something to speed up and I apply the same amount of force, if I have too much mass, I can reduce the mass, right, to make it speed up, or apply more force, right? So I can manipulate any of these variables to change either the acceleration or how fast it speeds up. I can manipulate the mass to either reduce the amount of force I need to move it or to make it speed up. And in terms of the force, if I apply more force, I can either make it speed up or I can move more mass. Does that make sense? Okay. So, I'm going to show you guys a video. I can't add it to the YouTube video, but I'll explain the clip really quick. Does anybody here ever watch the TV show Gilmore Girls? Okay, it's my favorite TV show. So if you don't watch it, we're no longer friends. I'm just kidding. There's a scene in the show where one of the characters gets a pedicab, you know, like the cabs where they carry people in the carts, and it's a bicycle, right? Like the one person is riding a bicycle, but there's people sitting behind them. And he's trying really, really hard to carry these people. But there's one of him and two of them in the car. And so they're really not going fast anywhere. So I'm going to show you the clip, and then I want us to brainstorm about how we could make adjustments to change the motion of the object. My question is, how could we make him accelerate faster? What could I do? How could I manipulate the other two variables to make him change his acceleration? Lucas. Add another person where? So what would I be changing really? Well, okay, in order to change the speed, but I would be applying more what? No. You can phone a friend. So what would I do with the mass to make him go faster? If I want him to go faster, how would I affect? Remember, the mass is on the back of the car. The force is on the front. The pedaling. So how would I change the mass to make him go faster if I'm not changing the amount of force? Take some of the mass away, right? I could take one person off. What could I do to the force to make him go faster? In terms of what? To the back of the cab with the mass, or to the force in the front of the cab? So I could double my force, right? So he could either add more force, so pedal harder, or have somebody who could pedal harder, right? Or get rid of one of the people and have less mass in order for him to accelerate. Does that make sense? Do you see how we're manipulating the variables to change the motion of the object? So this is where the math comes in. I'm going to give you guys two examples. One is where we're multiplying and one is where we're dividing. The first one, we're going to solve for the force. So how much force will it take to move an object that is 10 kilograms? How much force would it take to make that object accelerate or speed up at a pace of 5 meters per second squared? I want to know how much force would it require for me to make an object that is 10 kilograms accelerate or speed up 5 meters per second squared. So all I'm going to do is substitute, just like math, right? Do I know my force? No, so I'm just going to put my F there. Do I know my mass? What is it? No, in this problem, honey. That's what the mass is? What's the mass? 10. What's my acceleration? So what's my force? 50 what? What is 50 newtons. Very good. So in order to make an object that is 10 kilograms accelerate at 5 meters per second squared, I must apply 50 newtons of force. Yes, ma'am. That's an S, seconds. That's all. This is the other one. Maybe that is the example. What if I know, yes? No, just leave it blank. We'll put it, we solved it down here. What if I know my force? My force is, I'm applying 60 newtons of force to an object that is 5 kilograms, but I want to know how fast I'm going to make it accelerate. I want to know how fast I'm going to make it accelerate. So I'm going to, every single time, write F equals ma. Every single time. So I don't forget anything. If it helps you to write the arrows, what would go under my F? What would go under my F, Bobby? I'm waiting on Bobby. Bobby, what would go under my F? Can one of my mobile friends help us out? What would my F be, guys? What's my force? Zuri?
60 newtons.
Thank you very much. My mobile friends, I don't know what's going on, but you should be participating. Do I know my math? Yes, what is it? 5? Do I know my acceleration? No. How do I figure out my acceleration now? How do I figure it out? Braylon? Yep, whatever I do to one, I do to the other. So my acceleration is, what's 60 divided by 5? Nope. 6 times 6 is 36. 12. This is why I said you need to practice your multiplication and division. I will have to divide if I'm looking for mass or acceleration, multiply if I'm looking for force. So you need to be prepared to work on that multiplication. If I want to increase the amount of it speeds up, I need to change either my mass or my force, right? Those are the 3 variables I have control over. Does everybody understand that? To move a mass that's twice as much, I need a force that is twice as heavy. To make it speed up twice as much, I need twice as much force. Yes. That was, yes. So the unit, because acceleration includes both speed and direction, is considered like a vector quantity. Meters is how far it's moving, and then per second squared. So it's like per second, because I'm not just talking about just speed. I'm talking about how fast it's moving in a specific amount of time. If that makes sense. Okay. All right, and our third law, this one is my absolute favorite because it applies to literally everything in life. If you look at our behavior plan for here at school, right? It says, for every action, there is an equal and opposite reaction. That's actually Newton's law of motion, but it applies to everything. If you hit your sister, equal and opposite reaction, they're going to either hit you back or you're going to get grounded, right? If you are not following the classroom expectations, equal and opposite reaction, you get a verbal warning. You do it more than once, sea change. You do it 3 times, reflection and apparent contact, and then 4 times a referral, right? Equal and opposite reaction. And so in motion, this looks a little bit different. Other than behavior, if you think about it, if I put more time into studying for this unit test, what will my equal and opposite reaction be? A better grade, right? The more time you invest, the better the grade. If you don't invest time, your grade's gonna suffer. So this is pretty much like it's like the law of karma. If you think what goes around comes around. Well, Shakespeare said it differently. He said the wheel has come full circle, but the idea is like for whatever I do, there is a consequence, and that applies to motion too. I'm not acknowledging that right now. Here's my example. How many of you have ever been canoeing or kayaking? Okay, when you are canoeing or kayaking, I'll move it back in a second. When you are canoeing or kayaking, I have my oar, or my if you're canoeing, it's called an oar. It's a paddle if you're kayaking. If I want my boat to move forward, so the boat is moving forward, what direction am I paddling? What direction am I paddling, Lucas? Which direction am I pushing? If I want the boat to move forward, is the paddle pushing this way backwards, or am I pushing it this way forward? It's moving backwards. So if I want the boat to accelerate forward, I have to push the paddle backwards. Same thing when you're swinging. Don't you push your legs backwards to move forward? When you're running, everybody stand up. Just walk. Don't you feel the ball of your foot pushing you backwards as you move forward? The ball of your foot pushes backwards to move you forward. The ball of your foot is pushing back. So I push the paddle backwards. When you're swimming, you are pushing the water behind you. So our examples could be a canoe or a kayak. Swimming is an example. Can anybody think of anything else other than the bike? Because the bike is kind of hard. If you believe it or not, you're pedaling forward, but the tires are actually pushing backwards to propel you forward. Oh, sorry, swimming. I meant swinging. Thank you. Swinging. Can anybody think of any other examples? What about track? You push off of the earth to move forwards. Absolutely. Like little bits. Like I've gotten pictures of myself when both my feet are in the air. Let me see. Like here's one. So this is from this Saturday. So like, see if you look at Mr. Johnston. But if you look at my feet, Both my feet are off the ground. So whoever took this picture got me right as I was like right as I had potential energy to fall back down, right? I don't know. He's being a nerd. All right. So remember, what I want to apply this to is that all these are happening at the same time. I'm going to use the canoeing example. My canoe or my kayak is going to stay at rest until I apply a force to make it go forwards. If I have more people in my kayak, what do I need? More force. Thank you. And if I want it to move, I have to paddle backwards to make it move forward. So all of these are happening at the same time. Got it? All right.